Hello, this is Professor Isha P. Galgalikar. We are going to discuss today laminar flow, Hagen poiseullis equation and its application. So laminar flow, we already know that it is a viscous flow. It is sheet-like flow, that is one layer of fluid slides over another layer of fluid. Reynolds number is less than 2000, and when the fluid is moving very slow, then generally the flow situation is called as laminar flow. So let us now derive the Hagen-Poiseuilles equation. So in this figure we can see that there is a pipe. This is the direction of the flow which is shown here. So this is the direction of the flow which is shown here. A pipe is given and a small section is selected which is A, B, C, D. Now there are three forces acting on this. One is a pressure force. First force, pressure force acting in this direction. So its intensity is small p and it is acting on the circular element. We can see that this is the pipe and this is the circular element of thickness dr. So its area is pi r square. So total pressure force is p pi r square acting normal to surface AB, and in this direction total pressure force is p plus delta p delta x into pi r square, because the length of this particular section selected is delta x. One more force is acting which is offering resistance to the flow, and this is called as shear stress, and this is because of the viscosity of the fluid. When we have viscous fluids, then we will have shear force which is acting between the fluid layers, because all the fluid layers will slide over each other with different velocity. So tau is the shear stress, and it will act all over the circumference of this circular selected section. So 2 pi r is its circumference, and for length delta x. So total force is tau 2 pi r delta x. Now for equilibrium conditions, we will have the summation of all forces is equal to 0. So we will get for equilibrium conditions p pi r square, which is acting in right hand direction, that is in the direction of the flow, minus p plus del p by del x delta x into pi r square. This is acting normal to the direction of the flow, then minus tau 2 pi r into delta s, because this is also acting against the direction of the flow. If we solve this equation, then p pi r square and p pi r square, this p will multiply with pi r square, so this will cancel out. So finally, if we solve this equation, we will get tau is equal to minus del p by del x into r by 2. In the previous figure, now you must have noticed one thing, that total radius of this pipe is capital R, while small r represents the radius of this section. So I may have different velocity. Small r will vary. If I select a section with this much height only, then I will have small r here. So small r will vary while capital R remains fixed. So from this we get the shear stress distribution diagram and velocity distribution diagram. Velocity is maximum at the center of the pipe and it is 0 at the boundaries, while shear stress is maximum at the boundaries and it is 0 at the center. Here we have maximum velocity at the center and 0 at the boundaries. So this is the velocity distribution and shear stress distribution in a pipe. Now we also know that tau is equal to mu du by dy by Newton's law of viscosity, where y is generally measured from the pipe wall. Hence, from the previous figure, we can say that y is equal to capital R minus small r. And since capital R cannot vary, so if I say I want to find out dy, then dr, that is d capital R, will be equal to 0. It cannot vary. So I'll get dy is equal to minus dr, and I'll put it in the equation of the tau. Tau I will get minus mu du by dr. While equating both the taus, we will get the first shear stress that we have derived and the second shear stress. Minus mu du by dr is equal to minus del p by del x r by 2. From this we will get du is equal to 1 upon 2 mu del P by del X R dr. So du, we have got du, so we will integrate it and then finally we get equation of u, which is here velocity is represented with u and it is not represented with v. So we'll get equation of u, which is 1 upon 4 mu del p by del x r square plus c. C is the constant of integration. Now by the condition when small r is equal to capital R, u is equal to 0. We have seen that at boundaries velocity is equal to 0. So when small r becomes capital R, that is the boundary condition. Velocity is equal to 0. So putting this condition in equation 4, we will get u, we will put 0, we will get the value for c. So c becomes minus 1 upon 4 mu del p by del x r square. Finally, if I put this again in equation 4, value of c, I'll get final equation of velocity, which is equal to minus 1 upon 4 mu del p by del x capital R square minus small r square. Yes, so now this u will vary. While if I change this small r, I may have different values of small r. R is equal to 0.5 meter, sometimes R is equal to 0.25 to 0.25 meters sometimes. So this value of u will change and you can change for different values of small r. Similarly, if I want to find out u max, in the velocity distribution we have seen that maximum velocity occurs at center of pipe. So at center of pipe the small r becomes 0. So if I put small r is equal to 0, then I'll get the u max, that will occur at the center of pipe. So it will become minus 1 upon 4 mu del p by del x into capital R square. Small r will become 0. Again, if u max, I select this minus 1 upon 4 mu del p by del x into capital R square as u max. U can be written in form of u max as u is equal to u max. U is equal to u max 1 minus small r upon capital R whole square. Similarly, there is one more velocity. We have seen two velocities u and u max. So similarly, one more velocity is there, which is u average. So u average will occur at only one radius. That radius we will have to find out, but there is one relationship between u average and u max, which is equal to u average is equal to u max upon 2, or half of u max is equal to u average. U average is generally represented by u bar. So now we have seen three types of velocities: u bar, that is u average, u max, and only u. Okay. So u max is known to us. So u max by 2, if I take, then I'll get u bar. So u bar becomes minus 1 upon 8 mu del p by del x r square. So from this I can find out the pressure difference. So minus del p is equal to 8 mu u bar upon r square into del x. And if I integrate it from p1 to p2, that is one position to second position, and for some length x1 to x2, I can derive p1 minus p2 is equal to 8 mu u bar L upon r square, where x2 minus x1 is taken as the length of the pipe. So final equation becomes p1 minus p2 is equal to 32 mu u bar L upon d square, where d is the diameter of the pipe, L is the length of the pipe, u bar is the average velocity, mu is the viscosity, p1 minus p2 is the pressure difference. So now we have seen this. So let us discuss. Okay, so we have seen this. In the next lecture, we will see one problem based on this. Thank you very much.